Welcome to this tutorial on using shader programs in 3D games. Today, we'll dive deep into the world of graphics programming, specifically focusing on shader programs. But before we get started, let's discuss the importance of shaders in 3D graphics. In modern video games, shaders play a critical role in how objects are rendered on the screen. They enable developers to control the visual appearance of objects, apply realistic lighting effects, and create stunning visual effects that contribute to a game's atmosphere. To illustrate the concept of shaders, we will be using the OpenGL API along with Java. However, the fundamental principles of shaders apply across various graphics APIs such as DirectX and Vulkan as well. Let's start by exploring the components we need to create a basic application using shader programs. First, we're going to set up a basic OpenGL context using LWJGL, a lightweight Java library that provides bindings to OpenGL. This code creates a basic OpenGL window setup. Let's break it down a bit. The run method initializes GLFW and enters a loop that will render the window until closed. Now that we have our OpenGL context ready, it's time to write our first shader program. A shader program consists of two main components, the vertex shader and the fragment shader. The vertex shader processes each vertex's attributes, while the fragment shader determines the color of each pixel. Let's create a simple vertex shader that transforms a 3D point by applying a model view projection matrix. This vertex shader uses a uniform variable MVP to transform input vertices. You can observe the use of layout, location equals 0, which indicates that this input corresponds to the first attribute. Now let's create a simple fragment shader that colors the pixels. The fragment shader outputs a constant color, orange in this case, for every pixel. To utilize these shaders, we need to compile and link them into a shader program. Let's implement functions to do this in our Java application. We've created a loadShader function that reads shader code from a file, compiles it, and checks for errors. The createShaderProgram method links the vertex and fragment shaders into a single program. Now let's integrate this into our main application loop. Now that we are using our shader program in the loop, it's time to define the geometry we want to render. For simplicity, let's create a triangle. We will need vertex buffer objects, VBOs, to store our geometry data on the GPU. The above code creates a triangle using vertex array objects, VAOs, and vertex buffer objects, VBOs. We define the triangle's vertex positions and upload them to the GPU. Let's integrate the rendering of this triangle into our main loop. In the updated loop, we bind the VAO and call GLDrawArrays to render the triangle. If you run the application now, you should see a triangle rendered in the window. The color will be determined by our fragment shader. Next, let's extend our shaders to incorporate a uniform transformation to manipulate our triangle. We will implement a simple rotation for demonstration. First, we need to add a rotation matrix to our vertex shader. We added a uniform float angle to the vertex shader. This will be used to set the rotation angle. Now, we will also need to update the uniform in our main loop. In the updated loop, we increment the rotation angle and pass it as a uniform to the vertex shader. Now when you run the application, you should see the triangle rotating. Now that we have a basic understanding of how to create shaders and apply transformations, let's add some lighting effects to our triangle. We will create a simple lighting model in the fragment shader that lightens the triangle based on its position relative to a light source. In the fragment shader, we calculate diffuse lighting based on the dot product between the surface normal and the direction to the light source. Next, we need to pass the light position from our main loop. In this code snippet, we pass the light position and camera position as uniforms to the fragment shader. If you run the application, you should see the triangle changing its brightness based on the lighting calculations. Now, let's summarize what we have covered so far. We started by setting up an OpenGL context using LWJGL, created a basic shader program, and managed to render a rotating triangle. We also introduced simple lighting effects, showcasing the versatility of shader programs. To conclude our tutorial, let's consider extending this example further. You could experiment with different types of lighting models such as Phong or Blend Phong, explore texture mapping, or even implement shadow mapping for more intricate visuals. If you enjoyed this tutorial and found it helpful, please consider subscribing for more content on Java programming and game development. Leave any questions or comments below, and I will be glad to assist you. Thank you for watching.